Today, I'm delighted to present our joint work, The Cost of Performance, Breaking ThreadX with Kernel Object Masquerading Attacks. This is a collaboration among Southeast University, Drexel University, Anhui University of Technology, and Lowell. As background, real-time operating systems, or RTOSs, are widely deployed in embedded and IoT devices. As shown in this table, we can see only ZephyrOS and ThreadX provide comprehensive security protection mechanisms among the state-of-the-art RTOSs. ThreadX, however, applies aggressive performance optimizations, especially in parameter sanitization, and that's where our story begins. In this slide, we break down the parameter sanitization of ThreadX. Unlike Zephyr, ThreadX uses performance optimizations in parameter sanitization. There are two key differences between ThreadX and ZephyrOS. First, instead of directly validating the values of kernel pointers, it validates the address range of kernel pointers, and then it checks the field required condition field inside the pointed object. This shortcut is faster, but as we will see, it opens up vulnerabilities. Our key insight is that malicious user threads can mimic expected condition fields by modifying specific kernel object fields. This lets an attacker can trick ThreadX into believing a forged kernel object is valid. We will show an example for the vulnerability of ThreadX, as shown in the figure below. If the modifiable fields of kernel object A align with the condition fields of kernel object B, then the kernel object A can be used to forge a valid kernel object, bypassing parameter sanitization and enable exploration of kernel object B. To achieve this, we first invoke a system call and set A's modifiable fields to values that will satisfy B's checks, and then we issue a second system call invocation, which will treat the modified region as a valid kernel objects. As we can see, the result is creating a forged kernel object that overlaps the modified memory. Building on this vulnerability, we design a new powerful attack, which we call Kernel Object Masquerading attack, or KOM attack. KOM is essentially a confused deputy attack carried out by carefully training system calls. By conducting KOM attacks, the attacker can achieve privilege escalation and ultimately arbitrary memory access. Next, we will break down how a KOM attack works. KOM is consisted of 4 steps. I will explain each step below. We begin by creating or identifying the malicious and compromised kernel objects. These objects are either be existing kernel objects or newly created through operated system calls. The malicious kernel object must have at least one modifiable field, while the compromised kernel object must contain a pointer that can be dereferenced. Next, we aim to create the initial forged kernel object. To achieve this, we invoke a system call to modify a modifiable field of the malicious kernel object, and setting it to a chosen kernel object type ID. We also fabricate a pointer that points to the selected type ID, thus creating a forged kernel object referred to by this pointer. This forged kernel object, which has a valid type ID, will contain at least one modifiable field. Then, we create sequences of forged kernel objects to override fields in the accomplice kernel object. By invoking appropriate system calls with the pointer to the initial forged kernel object, we modify its modifiable fields. It is important to note that different system calls can be used to modify different fields of the kernel object. This process allows us to create multiple forged kernel objects of different types from the initial object. These new forged objects can in turn be used to create additional forged objects, and this process can be recursively repeated. By generating multiple sequences of forged kernel objects, we can target the pointer and other condition fields in the accomplice kernel object. Once the target pointer is overwritten to point to sensitive data, and the condition fields of the accomplice kernel object are adjusted accordingly, the pointer can then be dereferenced through a system call. For example, if the pointer is directed to the MPU control register, the MPU can be disabled, allowing an unprivileged thread to access kernel memory. So together, these four steps turn a design shortcut in ThreadX into a powerful attack primitive. Although Corm is powerful, manually mounting such attacks is tedious. Therefore, we developed an automated framework including three phases: symbolic execution, candidate object type selection, and generate system call sequences generation. These three phases is to automate Corm attack construction. In phase 1, we use an symbolic execution approach to filter out vulnerable system calls. We first convert the ThreadX source code to LLVM IR to enable symbolic execution. Then, by symbolically executing each system call, we inspect the memory operations, and we can identify all modifiable and condition fields within the kernel object based on the memory write operations. These fields are crucial for generating system call sequences for our attack. For modifiable fields, we determine their relative locations by resolving memory address inspirations. However, automatically identify condition fields from path constraints is challenging, as they often involve complex arithmetic or logical expressions. Analyzing all path constraints requires a parser capable of handling diverse expressions and resolving pointer expressions. While this process demands significant engineering effort, our evaluation shows that the number of path constraints is limited to no more than 6, so allowing us to manually deduce condition fields for each system call. By analyzing the system call's modifiable and condition fields, we can classify a system call as exploitable for Corm. In phase 2, we identify which objects can serve as malicious or accomplice kernel objects. For kernel object types, we pick types with modifiable fields and fully controllable pointer dereferences. We prioritize pointers with fully controlled pointer dereferencing, which enables arbitrary memory read or write operations. When dereferencing these pointers for a memory write, the data return is either assigned via a system call parameter, or a member variable within the kernel object, both of which can be controlled by the attacker. The pointers used in memory read operations are similar. However, it is important to note that other pointers, such as those dereferenced to write fixed values, can still be exploited strategically to cause significant impact. And for the memory location delimitation, we can either use allocator return addresses or reverse engineer object pointers in memory, such as a stack or heap. This narrows the scope for later exploration. In phase 3, we target feasible sequences generation. In theory, choosing the optimal syscore sequences is an NP-hard problem. Fortunately, we find that the number of vulnerable system cores is limited. This allows us to use deep first search, checking modifiable and condition fields at each step, and purling infeasible branches. In this way, we can generate feasible system core sequences for exploration. Now, we have covered all our methods. We move on to the experiments. Our first research question was, what system cores can be used to perform COM attacks? We found 31 out of 60 system cores can modify kernel object fields, while 70 can set fixed values, and 30 allow parameter-driven arbitrary modifications. Both categories are exploitable and leading to data corruption or kernel crashes. And this shows that ThreadX exposes a bold attack surface for COM attack. Our second question is, can our attack be effective in various attack environments? The answer is yes. For example, by chaining module allocate and timer create, we can iteratively create project timer objects. This allows us to override multiple consecutive fields in memory. In this way, we realize arbitrary memory write using only legitimate system cores. Our third question is, which object type are exploitable for kernel attacks, for COM attacks? After our analysis, we found all types except mutex can serve as malicious objects, since their fields can be modified to designed values. For accomplice kernel objects, every type works, since they all enable fully controllable pointer dereferencing. In fact, linked list operations in ThreadX make pointer dereferences particularly powerful. In this left figure, we show a system core of QSend. It is an example code for fully controllable pointer dereferencing. We can see by dereferencing the Q kernel pointer, we can write the arbitrary memory content through the system core parameters. Our fourth question is about efficiency of our symbolic execution engine. With our optimized symbolic execution, we found most system cores can finish under 1 minute, and the mutex put was the slowest, and it takes about 9 hours due to many branches and loops in the symbolic execution. And when system core did not terminate normally, this is because of the constraint solving issue we found in this system core. There are many constraint solving problems. But overall, our approach achieved high coverage within the practical resource limits. Our final question is, what are the real-world implications of our COM attacks? We validate COM on STM, OliMax, and Wilderness Labs boards in addition to QMU platforms. We successfully mounted COM attacks that achieved arbitrary memory access and even disabled the MPU. Our experiments confirm that QoM is practical on real-world hardware, undermining core security guarantees and posing serious risks to auto systems. To summarize, we have shown that performance-driven shortcuts in ThreadX parameter sanitization open the door to powerful QoM attacks. Thank you for your attention. Please feel free to reach out via email if you have any questions.